Our next speaker is Dr. Michael Ma, postdoctoral researcher at the STU Center for Energy Informatics at the University of Southern Denmark, where he also completed his PhD in energy informatics recently. And his work sits at the intersection of industrial digitalization, AI for industry, and data science. Today he will present us the Decode project, a project developing data-driven best practices for energy-efficient operation of industrial processes, illustrated through a case study on cheese powder drying. Michael, the floor is yours to share the presentation and start presenting. Thank you.
Yeah, thank you, Florian. I will share my screen. Yes, it's. Hello, everyone. I'm Michael from STU Center for Energy Informatics at the University of Southern Denmark. Today, I will present our research project called Decode. And in this project, we use AI-driven methods to analyze the industrial best practices for improving the energy efficiency in industrial processes. It's me. I'm the postdoc researcher at the Center for Energy Informatics, and my research focuses on data science and artificial intelligence for industrial digitalization, and mainly focus on the improving the industrial energy efficiency and production qualities. This is where my department from. We are in a city called Odense in Denmark, and our center's research focuses on developing the digital solutions for increasing the intelligent use of energy in smart buildings, smart cities, smart industries, energy networks, energy ecosystems, and energy digital infrastructures. Today, I will present the Decode project. The full name is the Data-Driven Best Practice for Energy Efficient Operation of Industrial Processes. And in today's presentation, I will introduce the overview and the motivation of the project, and then I will introduce the details of one case study in cheese powder production in this project, and then I will summarize the contributions of the case study and the total project. This project is a long 4-year project, and now it's the final stage. We will finalize the project within 3 months. In this project, we have 4 industrial partners. Fellow of mine help us to collect the data and manage the data from the end users. And Innovatech is an IoT company which help us to install the sensors and collect and manage the physical sensor data in the end users. And Vanima BM and Lactosan are 2 industrial end users. Vanima BM is Nordic largest foundry, and Lactosan is the cheese powder company that I will introduce in today's presentation. Next, I will introduce the motivation of this project. In Denmark, we target 70% of the CO2 reduction by 2030 and achieve the climate neutrality by 2050. So we should focus on reduce the CO2 emission and reduce the energy consumptions, especially in the energy-intensive manufacturing. However, in today's manufacturing and other industrial sectors, despite they have extensive sensor data, but many of the companies do not deeply make full use of the data, so they cannot link the energy you use to their industrial production decisions. And in their system controls that rely on the local heuristics rather than the data-driven optimization or the improvement of their operations. So it's very important to explore the digitalization and the data-driven technologies that can analyze the energy efficiency and the energy flexibility potential in many industrial sectors. This project aims to develop an energy IoT cloud platform that combines multiple technologies of IoT, big data, edge computing, artificial intelligence, and digital twins to support the production industry's evaluation and adoption of the best practices for optimal operation of the entire production plant. And my work focuses on the uh, data processing, especially adopting and developing the AI-driven algorithms and frameworks to analyze the energy efficiency in industries and so support the decision making to improve the energy efficiency in the industrial processes. Today, I will introduce one case study uh, in Lactosan. Lactosan is an international Danish producer of the cheese powders, and in the food manufacturing, the drying tower is one of the key processes that consumes a large number of energies, including the heatings and the electricities. So in this case, we collected the data from the sensors installed from the drying towers and some production order records that recording the start and the end time of the products and for example the weightings and the weight and the production qualities of each orders. We also collect the order level and energy costs, including the electricity and the heating consumptions for each orders. In this case study, I did develop it's called causal explainable AI for identifying drivers of industrial energy best practice. In this framework, I utilize the explainable AI algorithms and the data-driven causal inference algorithms to make recommendations to improving the energy efficiency and adopts the energy best practice operations. Mm, before start to process the data collected from the real world cheese drying towers, we should transform the raw process data into the batch level data set, because in this study, we didn't process the time series but analyze the batch level data. And in this case study, one batch means one production or order recorded by the factories. All the collected sensor time series are cleaned firstly by remove the missing values and the outliers, and then the batch in the cheese powder productions are identified based on the information provided by the company, and then the statistical summaries of the time series of operational variables are calculated for each batch. Then we have over 350 production batches, and in each batch we have over 135 features. Next, I will introduce the developed framework for you're utilizing the explainable AI and the causal inference algorithms to support the decision making in energy-based practice in the industrial processes. After collect the industrial data and constructed the batch level data set, we should first define and identify the energy best practice in the operations. In this study, two KPI are defined. One is called the energy unit, which is the energy consumptions per kilograms of the cheese powder in each batch, and the quality rate refers to the percentage of the valid cheese powder among all the produced cheese powders in one batch. Then for the two KPI, the Gaussian mixed model clustering are utilized to cluster the two-dimensional data set into 5 clusters. And then the linear decision boundaries are used to slightly modify the clustering results, because for the industrial partners, they prefer to see the linear boundaries rather than the non-linear boundaries. So the linear decision boundaries is more clear and explainable for the industrial end users. Next, because we have over 100 features in the dataset, and it's too much for the causal discovery and the causal inference. So we reduce the dataset by using the sharp algorithm and combined with the predictions on the energy consumptions. Then about 50 key features are selected for the further causal inference. The in the causal inference process, we selected two data sets, including the data set involving all batches and the batches in cluster 0 and the cluster 1. We learned the causality structures in each data set, and we also analyze the root causes, which refers to the key causality drivers of the important variables regarding the energy efficiency and the production qualities. Then next, the symbolic regression is used to learn the functions that can explain the cause and effect relationships learned from the causality structures, and the equations can help the industrial end users to simplify the control process and understand how the one variable can affect the other variable in the complex systems. Next, I will show you some results in this 5-stage framework. The results will start from the clustering analysis. The left figure is the original clustering results, and there are 5 clusters in total, and the cluster 4 are outliers, so we excluded it for the further analysis. And then the linear decision boundary are learned through the symbolic through the linear regression algorithms to classify the data points. You use the clustering algorithms as ground truth, and then in the modified clustering results, we can see that cluster 0 have the batteries with high energy efficiency and the low production quality, and the cluster 1 includes the high energy efficiency and high production qualities. So here cluster 1 is identified as the benchmark of the industrial best practices in the cheese pod productions. And cluster 0 and 1 involves about more than 90% of the batches. So in the causal inference, we mainly analyze the data from cluster 0 and cluster 1. Here is the result from the causal inference. It is the first stage in the causal inference that is the causality structures in 3 data sets. The left one is the causality graph, which shows the cause and effect relationships, and the right figure is we marked the important variables and devices in the SCADA diagrams. Here the blue circles in the left figure shows the in the collective structures regarding the production quality, and here we use the temperatures in the drying tower as the key variables, and the red circle shows the causality structures for the energy consumptions, and the yellow circle are the remaining variables. Similarly, we have the causality structures for data set 2 and 3. Here is the results of the root cause analysis. Here, in this study, the root cause analysis refers to the data-driven intervention experiments that identifies the important causal drivers of the key variables. For example, here in these figures, we use the data set 1 as the baseline, and the data set 2 as the intervention data. And for example, in here in the figure B, the key variables is a different temperature T1, T2, and from the figure we can see that the sensor data of the TT413 are the most important variables that influencing the temperature in the drying towers. After identifying the cause and the effect relationships, we learned the equations through the symbolic regression. We choose the 5 key variables. The first 3 are the power data regarding the electricity consumptions, and in number 4 and 5, there are the temperatures that regarding the production qualities. Here the 5 equations are learned to find to quantify the relationships between the causal variables that influencing the electricity consumption and the production qualities. The figures here shows that the results of the symbolic regression have the high quality prediction results. Next, because we should make recommendations to the industrial and end users, so we need to transform the data processing results into the industrial practical insights and make the recommendations. Here, the recommendation is the suction fan behavior is the most consistent driver of the electricity consumptions in the cheese powder drying towers, and also the pressure of the back filters and the are important for the electricity consumptions, and for the inlet and outlet temperature in the towers, some CMO condition related sensor data are very important to control to ensure the stable and the reliable production manufacturing in the drying towers. So then we make recommendations to explain to the industrial and users how they can use the results in the report. In the factory, they should use the operations from the cluster one as a best practice benchmark in the operations. So they need to compare the operations into the operations from cluster one, and then they need to improve the control of the suction fans and some the pressures and the other CMO related devices to improve the stability and the reliability in the systems. So to conclude, this case study introduces an expandable causal and symbolic and data analytics that transform the industrial data into the operational knowledge, so that can guide the industrial and end users to improve the energy efficiency and the production quality to achieve the energy best practice in their real world operations. And in the future, we validate the causal findings with the real intervention experiments, and continue to communicate with the end users to see if the recommendations is really useful or not in their real operations. Then we will also develop some real-time monitoring tools and also integrate the symbolic regression equations into the systems to achieve real-time and better decision support in the in different scenarios in the different factories. Yes, this is my presentation today for the Decode project. Thank you.
Thank you very much, Michael, for this interesting presentation and your insights into this developing data-driven best practices in the cheese drying, powder drying case. So we have now not a lot of time left for questions, but I would still to have some discussion allow for like 5 minutes of questions. Do we have any questions from the audience? Please. No questions at the moment, so maybe you have some time to think about it for a moment, and I start with a question. So, Michael, in the end, when you were speaking about Outlook, you were talking about interacting also with operators and really also trying to come up with validation strategies for the causal graphs that you found with these interference experiments and so on. So my question would be, did you already in your project interact with operators while building your models, or are you already engaging in these discussions? And do you have basically agreement between your data-driven insights and what they want to, or can they interpret your results the same way, or do you diverge in your views?
In current stage, in this project, the objective is to we have written a detailed report and how to conduct the experiments, and then we send the report to the end users. And the agreement is that the companies will try to will check and try to im, uh, improve some of the operations based on our recommendations, and then they will give us some feedbacks.
Okay, so they are already trying to incorporate your suggestions.
I'm not sure what's the stage now, but we have sent them our recommendations, and we are waiting for their operations and feedbacks.
That's very good news. So, do you think also you were also saying here that it could be used for other food drying processes? Do you already have in mind some very good application process where you think you can translate your methodology quite quickly and it would also be applicable?
Because in this project we have another case study and another partner from the foundry. So we also do the similar methodological work on the foundry data, and also make the similar recommendations. And yes, and then we hope to design as I said in the future work, we try to develop the real-time monitoring tools in the companies. So to compare their current operations with benchmarking resulting from the clustering analysis, and then in the tools we can automatically show the recommendations how to adjust and more modify the current operations to make it close to the best practice operations.
Okay, thank you. Then I thank you again very much for your time and your presentation today, Michael. It was a pleasure.